Okay, so we have a kind of a library here of all of the operations we're able to use on a priority queue, and we want to use this in order to sort a sequence of numbers. So let's just say we want to put them in ascending order from smallest to largest. The idea here is that we could repeatedly insert items from the sequence into our priority queue, use the object and the key as whatever that number is. That way, when we repeatedly remove the minimum item, we're removing whichever item is smallest from our sequence. And then we can kind of put everything into our priority queue first, and then repeatedly remove everything out of our priority queue and just add it to the end of our sequence. So this is the main idea behind a generic priority queue sort, and you probably came up with something pretty similar to this as well. So we have, here's the input sequence that we're given, which isn't sorted yet, that we want to sort, and we have a comparator, which just means we have a way to compare elements in that sequence. So this could work for any sequence of items, as long as we have a way to compare them. We create a priority queue using that comparator, so this is initially empty, and then we'll repeatedly remove items from our sequence, just taking whichever one comes first in our sequence. So E is that first element in our sequence currently, and then we'll take that item and insert it into our priority queue using that same item as a key as well. So once we're finished with this, we will have executed this n times, right? So this is just once for each item in our sequence. We remove everything from our sequence and we put it into our priority queue. And then we take everything from our priority queue and we repeatedly remove whichever item has the smallest key, which will be whichever item is smallest, since we're using items as our keys as well. And then we just put that into the last item of our sequence. So once we were done with the first while loop, we would have emptied our sequence, and when we're done with the second while loop, we empty our priority queue back into our sequences again. So we execute this again n times. So this is nice because just having a priority queue already gives us a way that we can sort a sequence of elements. So this is an example of using a priority queue as an auxiliary data structure. Okay? So we're not returning or taking a priority queue, we're just using one internally. Now, the running time of this generic priority queue sort depends on what we're using as an implementation for our priority queue. So we can evaluate some of these. So for example, we have a sequence, we access the first element, we remove the first element, and we store that in a variable. We know we can do this in constant time, and we can check if our sequence is empty in constant time. But how long insert item takes, we don't know yet. It depends on how we implement this. Similarly, we know that inserting into the last position of a sequence, we can implement this in constant time. You can go back to the videos on sequences to see how we can do this. And we can check if our priority queue is empty, we can do that in constant time. All of the data structures, we can check what their size is or if they're empty in constant time just by maintaining a counter, which is initially 0, and that we increment anytime we add an item, we decrement anytime we remove an item. But we don't know how much it costs to remove the minimum from our priority queue until we know how to implement it. So the running time of this sort just depends on how we implement this, this data structure. And there's a few different ways that we could do it. So we're going to look at first just kind of a basic approach to this, which is we use a sequence in order to implement a priority queue. So we just have to show how we would implement those functions: insert item based on a key, remove the minimum, access whichever element has the smallest key, and what is the smallest key. So if we have a sequence, let's say we could use an unsorted sequence, which means if we are given, let's say, we want to insert the following elements in this order: 4, 5, 2, 3, 1. With an unsorted sequence, we would, not care if the sequence is ordered or not. We would just insert items as we get them. So if we're asked to insert 4, and in this case, I'm just showing what the keys are, okay? So we insert an item with key 4, we insert that item key element pair as the first element in our unsorted sequence. And then 5, so we put 5 next, and then 2, and then 3, and then 1. So there's no order associated with this. So inserting becomes pretty easy because we don't care where we put the item. We just put it, say, at the end of our sequence. So we can insert in constant time, but then those operations which find the element that has the smallest key, this would be more expensive because now we actually have to find where that item is. So in this case, we would have to scan and keep track of whatever the current minimum is. And again, I'm just showing the keys here, not the objects associated with them. But we would have to scan and check to see, okay, this is the current min, and then check the next one. Is this smaller than the current min? Is this one smaller than the current min? We would have to go through the entire sequence to know really which of these elements has the smallest key. So finding the item with the smallest key, either to remove it and return it, or just to return whatever the smallest key is, or whichever element has the smallest key without actually removing them, this will become our more expensive operations. So these will be linear time if we use an unsorted sequence. Now we'll see kind of in the next slide that if we run that generic priority queue sort and we use an unsorted sequence in order to implement a priority queue, this is called selection sort. You'll see this in the next slide too, but the idea with selection sort is we use this implementation of an unsorted sequence and we run that priority queue-based sort. And the reason why it's called selection sort is selecting whichever item is the smallest is kind of the bottleneck behind that sorting algorithm. Now, we could try and improve this maybe because we see that removing the item which has the smallest key, this is an expensive operation because we have to find whichever that item is. So we could try and keep track of, while we're inserting items, keep track of which one is the smallest. And this is the idea behind using a sorted sequence in order to implement a priority queue. So if we're given 4, 5, 2, 3, 1, these are the keys that we want to, keys and items that we want to insert into our priority queue. If we use a sorted sequence, then how will this look? First, I'm going to draw this kind of a few times. First we insert 4. Okay, 4 just by itself, this is already sorted. Then we have to insert 5. So we're going to compare 5 to 4, realize that 5 is larger than 4, so once we insert 5, I'm just going to draw this as the next sequence. We have 4, 5. And then we're given 2. So we'll compare 2 to 5, realize it's smaller, compare 2 to 4, realize it's smaller, and then find the appropriate place to put 2 right at the beginning. So as we insert items, we maintain an order to this sequence. So by the end of this, once we've inserted all items, we'll already have a sorted sequence of elements. So in this case, removing the smallest element is easy. This is constant time because this will always just be whichever the first element is. So we have, by using a sorted sequence, successfully sped up the cost of finding whichever element is smallest and removing it, or just checking to see without removing which key is smallest or which element has the smallest key. So we can do these operations in constant time using a sorted sequence. But now insert item takes a little bit longer because we actually have to find where we're going to insert it. So for example, in this kind of input where we have 4, 5, 2, 3, 1 was our input, when we go to insert 3, we have to compare 3 to each of these elements. In the worst case, we have to compare it to all of them. Maybe we're inserting the smallest element. So in that case, inserting an item is linear time because we have to scan through, in the worst case, all n elements in order to find where to place it. So this is kind of the more expensive operation. So if we use a sorted sequence in order to implement a priority queue, and we run that priority queue sort, then this is called insertion sort. And the reason why we call it insertion sort is because, in this case, inserting an item is the kind of bottleneck, that operation which takes the longest. So let's just see how fast really these sorting algorithms are based on our 2 different implementations of a priority queue, either using an unsorted sequence to implement all these functions or using a sorted sequence to implement all priority queue functions. So as I said, selection sort, this corresponds to running our priority queue sort using an unsorted sequence. So what would the total running time of selection sort be? So we know in our generic priority queue sequence, our first step, this is that first while loop, we empty out everything from our sequence that we're given, and we dump it into our priority queue. So we repeatedly call insert item. We call insert item n times. And then when we're done with that, we take everything from our priority queue and put it back into our sequence. So we repeatedly call remove min. So another n times we're going to call remove min. So we have our first while loop, and then after that executes, we have our second while loop. So if we use an unsorted sequence to implement this, then we know insert item is efficient. One call to insert item is constant time, because we don't care where that item goes. We just put it at the end. We don't maintain any kind of order to it. But we call this n times. So the total cost of that first while loop is big O of n, is linear. In our second while loop, we call remove min n times, but remove min is more expensive. So the first time we call remove min, I'm going to write this at the bottom here. The first time we call remove min, we have to scan through n elements that we have in order to figure out which one is the smallest. Then the second time we call remove min, we got rid of one item, so we have to scan through the remaining n-1 items. And then the next time, now we have one less item, and every time we call this, we decrease how many items we have, but we still have to go through each one of them in order to find whichever one is the smallest. So it will help at this point to remember that summation of this sequence. So adding up all of the first n integers, this is n times n plus 1 all over 2. We'll see this quite a bit. So this is total of big O of n squared. So our first while loop total takes linear time. Our second while loop takes total quadratic time, which means our total running time is big O of n squared. This is that dominant term. So selection sort is big O of n squared. This is how we can sort using a priority queue, but we use an unsorted sequence in order to implement that priority queue. Now, if we used a sorted sequence and we ran that priority queue sort, again, this is called insertion sort because our bottleneck here is inserting items, whereas selection sort, our bottleneck was in selecting whichever item was smallest. So let's see what our running time would be if we use a sorted sequence. So again, we call insert item n times, but in this case, insert item takes time proportional to however many elements we have. So in the worst case, we have n elements. Now each time we insert, we keep adding elements. So the first time we just have one element, and then we have two elements. And then once we insert, we have to scan through 3 elements to find where we should place that item, all the way up until n. So again, remember this is big O of n squared. And then in our second while loop, we'll call remove min n times, but at least this time, one call to remove min is constant, because we know it's going to be the first element in this sorted sequence. So our total running time is big O of n for our second while loop. So the time for the entirety of insertion sort is the cost of our first while loop plus the cost of our second consecutive while loop, which is big O of n squared. That's our dominant term here. So both insertion sort and selection sort, what we saw last time, run in big O of n squared. Now, both of these sorting algorithms that we've seen now, we can also implement in place. Now, in place just means that we're using only a constant amount of memory in addition to the memory needed for the objects being stored themselves. So that means that, let me put it up here, in place means that the amount of memory, the amount of space that we're using, this would be exactly equal to however much space we need for the data structure that we're given. So notice that this isn't big O of n, this is exactly n. This is because this is exactly the data structure that we're given. So we don't create another data structure to store anything. We use whichever one was provided to us. So we have the amount of memory used is however much memory the data structure we were given was using, and we have n elements, plus we have a constant amount of additional memory. So this is kind of the extra that we're allowed to use. So this is what it means for an algorithm to be in place. It doesn't use a lot of memory. So we could implement insertion sort and selection sort in this way, in place, without using an external data structure. So before we were using an external another sequence in order to implement this priority queue. We could implement this in place, meaning we just work directly on the sequence that we were given, which we want to sort. So I'm going to show how we would do that with insertion sort. We can do the same thing, a similar thing with selection sort. So the idea is we're going to use a part of the sequence itself in order to implement our priority queue. So we're going to grow our priority queue kind of from the left side. So our priority queue is what's in green. And the part of our sequence that we haven't gotten to yet or processed or inserted yet into our priority queue is in blue. So we keep the sorted portion of our sequence will be on the left in green. So initially we have just, this is what we were provided. This is our entire sequence. Okay? So we are given this sequence data structure here. Now we're not going to create a new sequence. I'm just showing these separately so you can see in each step what happens. But the idea of implementing this in place is we're going to work directly on this sequence. We're not going to create another sequence. We can only use a constant amount of additional memory, and usually this means we keep track of pointers or indices, and then we'll use those values in order to swap elements of our sequence. So in our first step, we know we can add 5 to our priority queue on the left. This is 5 just by itself is already sorted. We're kind of separating our sequence in this way. Everything on the left of this line has already been sorted. Everything on the right we haven't processed yet. So this is our sequence after the first step. We know that 5 just by itself, this item is sorted. Now we go to process 4. So we're going to compare the first item from our yet unsorted part of this sequence to the item immediately before it. So we compare 4 to 5, realize 4 comes before 5, which means we should swap them. So in the next step, we've swapped 4 and 5. And there was nowhere else where we could have compared 4 kind of to continue here. This was the last element. So we know now these two parts of just the first part of our sequence is already sorted, 4 and 5. Right? So now we compare the next item of our unsorted yet sequence, which is 2, to the item which comes immediately before it. And if at any given point in time when we're comparing, we find that this item is smaller than the item that comes before it, then we swap them. So we compare 2 to 5, we find 2 is smaller, so we swap these two. Then we compare 2, which is at this location now, to 4, we realize 2 is smaller, so we swap them. So 2 eventually gets moved all the way down to the beginning. So now we have 2, 4, 5. Now we compare again the next item. So for 3, we determine where does 3 belong in this sorted sequence. But again, we're working on the sequence that we were already provided. So we'll swap 3 with 5 because it's smaller. Now 3 is here. We'll swap 3 again with 4 because it's smaller. And then when we compare it to 2, we realize it's not smaller than 2, so we stop there. We don't keep going. So now this is our new sorted sequence. And then finally, with 1 at the end, we compare it to 5. It's smaller. 4, it's smaller. 3 and 2, and it's smaller than all of them. So 1 gets moved all the way to the back, to the beginning. So now that we've processed all elements of that sequence, we know that we have a sorted sequence. So this is the idea for an in-place insertion sort. We're using that same kind of method of inserting into a priority queue in order to sort this. But what makes this in place is that we're not using another separate data structure. We're working directly on the data structure that we were given, and we're just using a constant amount of additional memory in order to keep track of which objects we're looking at and then determine if we should swap them or not. Okay, we're going to see another implementation of a priority queue in the next video. I would suggest that you keep track somewhere of which sorting algorithms we've talked about so far and how efficient they are. So we have insertion sort and selection sort, and both of them run in big O of n squared time. And we'll see how we can make an even more efficient implementation of a priority queue using a heap, and that's in the next video. And as always, if you have any questions, post on Piazza and let me know.